right, so in today's video, I'm going to walk you through the process of predicting products of single replacement reactions. So the general form of our single replacement reaction is A plus BC yields AC plus B. Now it's not always going to be in that order, but I have an example here of one that follows this specific order. So we have nickel, which is our A, and we have lead nitrate, which is our BC. So nickel is going to come in, react with our lead nitrate. It's going to kick out the lead, and it's going to bond to the nitrate to produce nickel nitrate, and this should be a lowercase 3, not a subscript 3. So nickel nitrate, and then the lead is a product by itself. So basically any single replacement reaction is going to have that form of one element, a single element coming in and trying to react with a compound. And the ones that we are doing for the most part in this class involve metals coming in and exchanging for another metal. So nickel is a metal coming in and kicking out lead, which is another metal. So there are 3 steps to predicting these products. The first step is figuring out whether or not this reaction is even going to occur. And the way we determine that is by looking at the activity series. And we look at whether our single element A is above or below the element that it might replace in the activity series. And I'll get to that in a second. The next step is the same as for the double replacement reactions, to figure out what the predicted products are. So if we know that nickel is reacting with lead nitrate, then we know that the nickel is going to become a cation and is going to make a compound with nitrate, and lead is going to be left out. So it's a pretty formulaic approach, so it's fairly easy to figure out what the combinations of products are going to be. But the thing you need to remember to do is to rebalance the charges on the new compound that you've made. In the case of our example above, lead in the compound with nitrate has a charge of +2, because nitrate has a charge of -1, and we have 2 of them to balance with the lead. And it turns out that our nickel nitrate, in this nickel nitrate, our nickel also has a charge of +2. So it has basically the same formula as the lead nitrate did, just with nickel instead of the lead. That's not always going to be the case, depending on what the charge is on the ion of the new substance coming in. So you always have to make sure you balance the charges on your new compound. And then in the end, you're going to balance the equation if it needs balancing, and use coefficients in order to balance out, in order to follow the law of conservation of mass. So let's look at our activity series and do a couple of examples. So there are lots of different versions of the activity series. If you look online, you may find a version which has somewhat different elements than this particular set of elements here, but they're always going to be in the same order, because they're ordered from the most reactive compounds at the top. So these are not compounds, elements. So these elements are very reactive. They really, really, really want to lose or gain an electron. In this case, in the case of these elements, they really want to lose an electron and form a compound rather than sitting around as a neutral element. They really want to react with other substances. The ones toward the bottom of the table are going to be our least reactive. Okay? And the way this ties into our single replacements is that the ones at the top can replace anything below them. The ones at the bottom can be replaced by anything above them. It's sort of like a pecking order. So this, it's a ranking system. You could say this is our number 1 rank, and it's going to beat anything below it. Think of it like a March Madness bracket that it always goes to seed. There's never an upset. You're never going to have mercury coming up and kicking out lead. That's not going to happen. It's always going to be the other way around. The top ranked elements are going to beat out the bottom ranked elements to make the compounds. So let's do a couple of examples here. So I have aluminum coming in and reacting with my lead nitrate. Okay, so similar to the reaction earlier. So first thing we got to do is figure out, is this reaction even going to happen? So we look at aluminum on our activity series. It's right here, up pretty close towards the top. And then we look at our lead. So the aluminum is not going to replace the nitrate. It's going to replace the other metal. It's going to replace the lead. So we've got to find lead on our series, and here it is. And we can see that aluminum is above lead. So the aluminum ranks higher and is going to be able to kick lead out of its current compound. So the aluminum's going to come in, boot out the lead. The lead's going to go off by itself, and the aluminum is going to take its place. So our first reaction, our first product is going to be a compound between aluminum and nitrate. Now I'm sort of prematurely putting these parentheses here, and that's to remind you that NO3 is a polyatomic ion. The nitrogen and 3 oxygens are covalently bonded together, and together they have a charge of -1 as a single ion, as one NO3 ion. Our aluminum, if we look at the periodic table, we can see that aluminum in group 13 wants to lose 3 electrons in order to get to that stable electron configuration that neon has. That is its shortest route to achieving that stable noble gas configuration. So aluminum wants to make a 3+ ion. In order to balance out these charges, I can't just have one aluminum and one nitrate. I have to either use the crisscross method or just think about how many -1s do I have to balance out a +3. So if I want to use the crisscross, I take the number of the charge on my cation and I bring it down, and that becomes the subscript of my anion. And that is why I made sure to have the parentheses, because if I wrote it as NO3, that would mean that I had 33 oxygens and 1 nitrogen. I don't want to say that. I want to say that I have 3 nitrate ions. Okay? So that's why I need the parentheses around my polyatomics. So my final product would be written out as AlNO3. Now that's not my only product. This is not a synthesis reaction. Remember, the lead is being kicked out by the aluminum. So it is also going to be a product by itself. And with metals, if we just have the metal by itself, it doesn't exist in a molecular form, so it doesn't need a subscript. It's just going to be however much lead we have. So now, looking at my overall equation, I have aluminum plus lead nitrate gives me aluminum nitrate plus lead. But I have different numbers of nitrates, so I'm going to have to balance this equation. The way I'm going to do that is I'm going to put a 2, and I'm doing this in the short version. I'm going to put a 2 in front of my aluminum nitrate. That's going to give me 2 aluminums and 6 nitrates, because this gets multiplied by the subscript on each one. And if there's no subscript, it's just a 1. So it gives me 2 aluminums and 6 nitrates. Now up here in my reactants, I have 2 nitrates. In order to give myself 6, I need to multiply this whole thing by 3. So that gives me 3 leads and 6 nitrates. So now my nitrates are balanced, but I have 2 aluminums in my products and just 1 in my reactants. So I need to put a 2 here. And I have to balance my lead out between my reactants and my products, so I'm going to put a 3 here. That's about as complicated as it's ever going to get when you're balancing a single replacement reaction. Pretty straightforward, only have to make a couple of changes. So that's our final balanced reaction with our final products of this single replacement reaction. Let's look at another one. Let's look at silver coming in and reacting with potassium nitrate. So again, our first question is going to be, is this reaction even going to happen? Or are we going to put silver in with our potassium nitrate solution and they're just going to sit there and not react with each other? So let's look at our activity series. Ag, silver, is way down here at the bottom. That means it's the least reactive of the elements in this list. Potassium is all the way up at the top, which means it's the most reactive out of the elements in this list. So there is no way that silver from the bottom, ranked at the very bottom of the table, can come in and kick out potassium, which is the highest ranked. So this reaction is not going to happen. We are going to say NR for no reaction. We aren't going to have any new products, and we don't have anything to balance. So we're done with that one. So hopefully this example helped you out a little bit. And I may do another one of these for balancing equations in the near future. All right, thank you very much.